what I want to do is just talk a little bit, very briefly, about sort of the main ideas of the course and just a couple of other things. So some of this is kind of obvious, but it's probably worth saying now. So talk about modeling. I mean, that's kind of the focus of the course is on modeling, right? The idea is, look, a lot of problems in things like engineering design, statistics, machine learning, economics, management, goes on signal processing, all these kinds of things. You can express them as mathematical optimization problems, right? So, I mean, this is kind of obvious, right? But actually, you'd be shocked at how few people make it over that step. Um, and this business of, I mean, real problems are really multi-objective, but once you know about optimization, it's not a big deal to look at, to have something be a constraint or a trade-off between three things or something like that. I mean, so that's fine. Now, we focus on a canonical form where we identify one objective as infinitely soft and all others as infinitely hard. I mean, that's fine, but everyone should know that real problems, there's a trade-off among some of them. I mean, some are really non-negotiable, right? Like covariances should definitely be positive semi-definite, for example, right? Powers definitely should be bigger than or equal to 0. These are non-negotiable, but a lot of the others are not. And the main point is something like this, that roughly speaking, the tractable problems are the ones that are convex. That's kind of rough. And I mean, you could even go more, that you could make the radical assertion is that's not a rough statement, that's just true. And if you wanted to push the radical statement, I'm not sure I believe the radical statement, and I'm not sure if it has any implications even if you did, so I'm not sure it matters. You would argue that all the polynomial time solvable discrete problems, they all work because, say, some convex relaxation actually has zero duality gap, right? So you'd look at all the minimum, find the shortest path between 2 points in a weighted graph, right? Okay, well, you would say the convex relaxation of that has zero duality gap, right? I mean, that's a bit silly because then you ask the question, well, great, now that I know this, should I be solving, minimum distance in graph, shortest path problems that way? And the answer is no, go back and use the same method you were using before. So it doesn't really say anything. The other source of non-trivial problems that would appear to be non-convex and yet you can solve, and they are solved all the time, are obvious. They are singular values, eigenvalues, PCA. These are obvious, right? It turns out there is also a kind of a weird connection to convexity. For those problems, the dual actually is a semi-definite semi-definite program, and it has zero duality gap. There's zero duality gap for those, right? So you could even argue, I mean, that's a bit weird and extreme to walk up to someone and say, what are you doing, PCA or something? And you say, how do you know it works? And you go, well, I mean, I'm sure I'm getting the best, whatever, rank 12 fit or something like that. By the way, that's not the one we just looked at, the example, right? Sure I'm getting, how do you know? Well, it's the global solution and so on. It really doesn't help to say, oh, I can tell you why. It's because of some result in algebraic geometry that the semi-definite programming dual of your PCA problem has zero duality gap. That doesn't seem to me to be illuminating. It is true, but doesn't seem to me to be illuminating. Okay, so, all right. Now, if you have a non-convex problem, in general, you have two choices, and these are the two extremes. Actually, there's everything in between, and here they are. One is to give up is to actually replace solution with solution and then a little asterisk and then a footnote that says maybe, right, or not really, right? And it's just you're looking for a local solution, and these are extremely useful. There's lots of cases where this is very useful. I mean, engineering design, something like that. You really don't care if that is the lowest power design that meets all your specification, right? If it's low enough power or it's a 20% improvement over what you had 10 days ago, that's fantastic. And you don't sit around and worry about whether it's the global solution. Okay, so very useful. And these will have the same running time as convex problems, right? Now, at the other extreme, you have global optimization. And these will have exponential worst case runtime. By the way, in a lot of practical cases, they don't have exponential. I don't know what that means. Sorry. In a lot of practical instances, you can actually solve these to completion, and it's not so bad. right? So, and in fact, what really happens is anywhere where people actually do this, they have a timeout and they run something for a couple minutes and they quit, and you're really getting something in between. So, okay. One thing that's interesting is, and this is something that's come up, in the last like 20, 25 years, it's been a slow thing. If you accept linear programming, right, possibly quadratic programming, then it was it's what's this but just been in the last 25 years, people have discovered a lot of problems that actually are convex, or can be transformed to be convex, right? And that this was not, just not obvious. Although I have some advice to give you. So this is serious advice now. So, long time ago, I used to give a talk on control, and I would say, look, here are some problems in control that you can reduce to convex problems, and I'd show one and another and everything. And I thought, well, it would be good, I should show one that cannot be. So I showed one that I thought could not be. And I said, here's one, and actually, fortunately, in the slides, it said that probably cannot be reduced to convex. And it was something involving, finding a Lyapunov function and a state feedback gain at the same time. And I gave even a very good argument for it. I said, look, they get multiplied together, and that's never good for convexity. We know that, right? So it wasn't looking good. Everybody following this? And this is just in the spirit of, I just showed you 5 things that can be reduced to convex problems. I should show you one that cannot. Okay? So I gave the talk 10, 15 times. After the 15th time, somebody, Andy Packard at Berkeley, comes up to me quietly and he goes, can I show you something? And I said, oh, sure. And he takes out a piece of paper and he fills like about 4 lines at the top of it. And guess what? The problem I had not just then, but 15 earlier times to large audiences said was non-convex. He did some sick change of variables, right? That no normal person should ever have thought of. But there it was. Guess what? It was convex. It was 4 lines, right? And then I started getting, hyperventilating and so I quickly looked back at my slides, and sure enough, I was so lucky. It's the top of it said a problem that probably cannot be solved using convex optimization, and then I even had a footnote that said, as far as I know. So anyway, so let me tell you what the moral of that story is. If you're with friends, it's informal, say whatever you like. Okay? But if you're out in some other place, you don't look at something and say, here are the things that it seems to me reasonable for you to say in a semi-public setting. Here are the things you can say. You can say, that problem is convex or can be transformed or solved by convex optimization. That's okay, but if you know it's true. The second thing if that problem has not been shown to be NP-hard, you should be quite quiet in public or even semi-public. Okay? So that's my advice, because I've been a victim of this. So, all right, everybody got this? So, okay. All right. So, what are the theoretical consequences of convexity? Well, the simplest one is if you have a local optimum, it's global, right? And so that's, but by the way, that's a very shallow idea of why this all works. Because you explain this to someone, a lot of people go, oh, yeah, sure. No, that makes total sense, sure. It turns out that's not right. For example, there are optimization problems where all local optima are global and they are hard. Right, so this is not quite fair. This is okay if it's just if you want to give a 20-second version of why this is why. By the way, local optima are global. That goes back to something very early on in the class. One interesting question is, how can you conclude that from convexity, right? And the answer is really simple. What convexity allows you to do is it allows you to go from a local statement to a global one. Right? If I know the gradient of a function at a point, I can produce a global lower bound. That, if someone says, well, wait a minute, how could you possibly know that that's the best you could do? That's ridiculous. R100 is a big place. R1000 is a lot bigger. And that's the answer. And you say the answer is because of the mathematical properties of the functions involved, I can extrapolate from here and know something globally about it. Then you get duality and it gets more complicated, but that's basically where it comes from. So there's an extensive duality theory. What is that? Lots of ways to think of it. But one way is to say it's just a very systematic way to derive lower bounds on optimal value. That's what it is. Right? By the way, that alone is a very good, you have a problem, and now you say, well, I mean, if you can't solve it or something like that, especially if it's non-convex, it's even interesting. Then you say, here are some lower bounds. If you come up with things that satisfy these, and that should be something you should be able to do, then you'd say, then this is a lower bound, right? That's actually very valuable often. And in the case of convex, you get necessary and sufficient conditions for optimality, and you get cool things like certificates of infeasibility and theorem of alternatives for inequalities, right? And for sets. That's the basis of lots of things, like for example, economics, right? Just to name one, right? So because everything's based on absence of arbitrage, right? So there's lots of other things like that. And of course, as a practical matter, you get something unbelievably useful, which is sensitivity analysis, right? So when you solve a problem for free, you get to find out how sensitive is that problem, how sensitive is the optimal value of that solution to any change in parameters, right? If you're doing engineering design, that's unbelievably useful because it tells you how much, for example, that power constraint is really limiting you, or your phase margin constraint. This will tell you exactly, I mean, at least in a perturbational sense, it'll tell you how much that's costing you, right? In statistics and fitting, this is also unbelievably useful, right? Because you say, well, I'm assuming my parameters are non-negative. Why? Because I think that the greater this feature is, I have prior knowledge saying that it must be the case that the probability of this classifier being 1 should increase, right? That's a non-negativity. If some of those things turn out to be 0 with a large Lagrange multiplier, that's telling you something. That's basically saying, guess what? If I could actually take that coefficient negative, I could really reduce the negative log likelihood. Everybody see what I'm saying? So, okay. And you have solution methods that have polynomial worst case complexity theory. That's with self-concordance, and it kind of varies, as you know, between sort of the practical and the theoretical analysis. Okay, now the practical consequences are, for medium scale problems, you can solve a problem in like 20 to 80 steps, roughly, right? Each of those steps is basically a least squares problem of the same size, right? So if you like, it's hilarious. We've come all the way back to 1802 or whatever it is, and someone says, what are you doing? I'm solving a problem. How are you doing it? Least squares. And you say, well, actually 20 or 30. I'm solving 30 least squares problems, right? But in this case, it's a different thing. Instead of like tweaking parameters and tuning stuff in an ad hoc way, you actually say what you want. Like, I want this thing to be positive. I want this thing to be in that range. And that tweaking of parameters is done in a very sophisticated way. Okay, so I'll move on. I should say that for people solving much larger problems, and that's basically anyone in machine learning, interior point methods are not used. These are small things, and there's a whole world of methods that can be used in those regimes. And there's actually several places where you can learn about that. So, okay. So let me say a little bit about, how do you use it? And this is just my idea, and it differs markedly from some other people whose opinions I very much respect. I'll say a little bit about what that is in a minute. So here's one idea. And it's, it has to do with the kind of problems I would look at and something like that. But it goes like this. The idea is you should use rapid prototype and approximate modeling, right? You start with simple models, small problem instance, and some inefficient solution method. And you see if it's promising. If it's not promising, then there's no need for you to worry about how to scale it. I mean, that's actually, in a way, that's a good outcome, right? Because you don't have to worry about scaling it. You can always do things like work out and simplify and interpret the optimality conditions and give an interpretation of the dual. That's always interesting at the least, and sometimes even useful. Another thing, although we talked only a little bit about it, we had a few problems involving integer variables and things like that, and there were hints of this. But my feeling is you should first learn convex optimization. Once you're fully certified in convex optimization, which you will all be by the end of this coming weekend, but once you're fully certified, then it's okay. Then you get more relaxed about it. And in fact, you can solve there's lots of non-convex problems you can solve extremely effectively knowing these tools. So I should say a little bit about this. So this is actually this idea of you start with small, simple models and then ramp up, that's very different than, for example, what people do at Google, right? So they have this big deal, which is you prototype at scale. You don't write some little tiny thing and, on your laptop or something. It's like the first thing you write runs on a data center. Okay, and the argument for that, and I think it's actually correct, is that a lot of things they're looking for don't emerge until you get to scale, right? And in that case, of course, it's completely correct. You don't sit around and type something into CVX and say, "Oh, hey, look at this," and then say, "No, now all I have to do is map it to." I mean, not to mention MATLAB and CVX are not real things, but even the analog of that, so there that makes perfect sense, and I think that's just a different set of applications and stuff like that, and I respect that as well. But just so you know that this seems very obvious, but there's plenty of people who completely reject it, and I think for what they want to do, completely correctly. So, okay. So I'll say a little bit about a few things, and then I'll just wrap up. So things we didn't cover are methods for large-scale problems, right? And there are tons of these. These will be covered in EE364B. Related to that is there's a whole set of mathematics we did not cover, which is subgradient analysis and a bunch of convex analysis, and these are related. Actually, these are all related, and in fact, so is this distributed convex optimization, right? So how do you solve these problems on distributed machines and things like that?